Yes, thank you for the introduction and thank you for having me here. This is joint work with Omar Fazi and Volker Scholz. How does that work? Ah, now we're good. Perfect. Yes, so first thing I'd like to say is it's going to be a theoretical talk, and I also have to apologize because I decided to present our ideas by means of a non-cryptographic problem. The reason just being that it's much easier to understand, I think, and I only have these 15 minutes. So I would like to talk about classical noisy channel coding. This is just about sending classical information over noisy channels, classical channels. And I would like to compare this to an entanglement-assisted version thereof. So the channel is still classical, but I would like to give quantum assistance. And in particular, I would like to study how powerful this quantum assistance is, how much it can help you to send information over the channel. And our method for doing that is we give a semi-definite programming hierarchy for understanding this difference. In particular, we give an upper bound on how much this quantum assistance can help to send information over the channel. And then I also want to briefly mention how these ideas are useful in cryptography, and in particular for studying randomness extractors. And here, I don't want to upper bound some quantum assistance, but the power of quantum adversaries, okay? Good, so let's start with the noisy channel coding example. So here on this slide, everything is completely classical, okay? So we have some noisy channel W, and so this is just some matrix of transition probabilities, which go from some finite set x to some finite set y, and we can think of it as like a noisy connection between two labs, right? Alice and Bob. And now what we want to do is we want to send the information over this channel. In particular, we want to be able to send k different messages over this channel. And of course, we want to do it as good as possible. So I would like to fix the number of messages we send, and I want to optimize the probability that we succeed, okay? And so what can we do? Well, we can encode here in Alice's lab. We can decode in Bob's lab. And we allow probabilistic encoders and decoders. So for every for every message you want to send, this is just a probability distribution over the input x. And the decoder here is for every y that the channel spits out, it's just the probability distribution over the messages I. Okay? And then the optimal probability that we can succeed for this transmission is given by this function, okay? I just optimize over all encoders, I optimize over all decoders, and then this is averaged over all messages, okay? So this is a bilinear optimization problem. It's linear in E and linear in D, okay? So just because we just had Graham's talk before, so I want to emphasize that I'm really interested in this one-shot picture, okay? So we have the channel once, and I want to optimize the success probability. So in particular, for those who know Shannon information theory, I'm not interested in some asymptotic capacity, okay? So in this Shannon information theory, one usually has many instances of a channel available, and one does some big encoder that acts on all instances simultaneously, and same thing for the decoder. And then one is interested in the maximal rate, the asymptotic maximal rate, such that the transmission succeeds with probability 1, okay? And then this is what is called the channel capacity, and as Shannon has shown, it's given by the mutual information between the channel input and channel output. But yeah, I'm not interested in that, but we're really interested in this one-shot setup. And this is, well, if you think about cryptography, we're usually also interested in this more channel setup. Okay, now let's throw in some quantum assistance. So the picture is still the same. Only thing that changed is that now we have some assistance here. So we have some arbitrary entangled state as a resource, okay? So if we only had this state, then of course this would not help us for transmitting information from Alice to Bob's lab. But if we have it together with this noisy channel, this combination of resources might be more powerful than just having the noisy channel, okay? So now, what can we do now? Well, the encoder is now not just a probability distribution, but it's actually a measurement. It's a general POVM. And same thing here for the decoder, okay? So this whole program here, this optimization, that gives us the optimal success probability. still looks basically the same. Just well, here in the objective functions, we now have these POVMs, E and T, and yeah, we also optimize over those. Okay, this is again a bilinear optimization, but a quantum bilinear optimization, because the variables are now matrices and no longer scalars, right? So if we compare this to the program that we had before, so only thing that changed is really that before we optimized over these scalar variables, and now we have to optimize over matrix variables, okay? And I want to emphasize here that we really want to allow arbitrary entanglement assistance, okay? So we also have to optimize over all Hilbert spaces and all states on these Hilbert spaces. So there's no bound on a dimension or anything. Okay, so now just as a comment here, since we don't give any bound on this assistance, it's in general not even clear how we can compute this quantity. So it's not clear if you can find an algorithm that determines this value in finite time, because in principle you have to optimize over all Hilbert spaces and all states and so on. Okay, but of course what I would like to do is I would like to study these two different success probabilities, the one the plain classical one and the other one the entanglement assistant one. So in particular I would like to know, is there a separation? How large can the separation be? Do we have good examples to understand that? Again, Shannon information theory, as Charlie Bennett mentioned in the last talk, the asymptotic capacity is actually the same if we allow entanglement assistant or not, okay? So if you're only interested in the asymptotic capacity, then this entanglement assistant is not helping us. But again, that's not what we're interested in, but we're interested in this more refined picture, and then there is a separation, okay? So Prevedel and co-authors, they gave this specific example, so that's just the input-output matrix of some specific channel, and they show that if we want to send one bit of information over this channel, okay, then they calculate that the classical success probability is given by 5/6, which is roughly 0.833, and they can also show that this entanglement-assisted success probability is lower bounded by 0.902, which is higher, right? So they do this by providing an explicit coding scheme that makes use of entanglement assisted, but only of two-dimensional entanglement assistance. Okay, so they use one EBIT to boost the success probability from this value to this value. And in these follow-up papers, it's also shown that this is optimal as long as we restrict to two-dimensional entanglement assistance. But of course, the question is, what is the actual value for this entanglement-assisted success probability? So we know that it has to be at least 0.902, but it could be as high as 1, right? So we don't really know that. And yeah, so in principle, how can you tell it's never 1, right? You have to optimize over all Hilbert spaces of all possible entanglement assistance. So what we do now, so this is basically the main idea of this talk. We give sorry. Wrong button. We give a hierarchy of semi-definite program relaxations that gives upper bounds on this entanglement-assisted success probability. Okay, so all these SDP1, SDP2, and so on, these are all semi-definite programs, and it's not so important what a semi-definite program is. In general, it's just important that one can efficiently compute these things, okay? I can put in the channel, I can put in the number of messages I want to send, put it in MATLAB or whatever, and it will give me the value. So there's no unbounded optimization going on here. And then moreover, this hierarchy also converges to the actual entanglement-assisted value here. But what happens is that these STPs get larger and larger, such that it's actually not efficient anymore to evaluate them. So in particular here, this is infinitely large, okay? But these first levels of the hierarchy, they might already be good upper bounds on this value, and maybe even tight, okay? So let's talk a little bit more about this. So this is just the bilinear optimization from before. So now, what are we going to do? Well, first thing I want to do is I don't want to optimize over tensor product encoder and decoders, but I would only like to assume that they commute. Okay, this is it's just a technical step. It's certainly a relaxation, because if I input here a tensor product, encoders and decoders, they will commute. Okay. And now the next step is that we relax this bilinear form over here, okay? So this is an idea that was used in the literature before, in the classical and in the quantum setting. And well, these are references. I'm not gonna read them all. But in the setting of Bell inequalities, this is also known as the NPI hierarchy, if any experts are in the room. But again, let me emphasize that we're not exactly doing that, but we're actually doing something better. But these ideas come from these references. Okay, so the basic idea is that one can see this bilinear form as part of a gray matrix, namely this matrix omega. So gray matrix, just a matrix of inner products, and it's by definition positive semi-definite. And this matrix omega I want to look at is just given by psi x u x v psi. These are the entries of the matrix, and these x's are just given by the e's and the d's. So these are the variables. And well, this, if we want, we can write this matrix omega into these 4 blocks, and this thing here that appears in the objective function is part of this upper right block here, right? So if for the entries where we have I equal to j, this is actually what's happening. And now all I want to do is, instead of optimizing over all psi e's and d's, I just want to optimize over all positive semi-definite matrices omega. Okay, that's a relaxation because, well, any combination, any valid combination of psi and d is defining me such a matrix. So if I optimize over all these matrices, it's a relaxation, certainly. Of course, I have to be a bit careful because I also have all these conditions on E and D. But if one does this, one can actually phrase these conditions as positivity conditions on this matrix omega. And if one does this, then one gets, because these are all positivity conditions, a semi-definite program relaxation, which is this STP1. Yeah, so this is just the program now. This optimization here of psi E and D is replaced by an optimization over all these matrices omega. And now the size of these matrices is defined by the size of the channel and the number of messages we want to send. But this is no longer unbounded. And then we have all these additional conditions that came from the additional conditions before, but the exact form is not so important. Let's go back to our example. So this is what we had before. Now let's see if this STP gives us a good upper bound. And so what we get, we can, as I was saying, we can put it in a computer and this spits out a value, and what it spits out is 0.908, okay, which is this 1/2 plus 1 over square root of 6. And then you see there is a gap between this 2 here and this 8, right? So the question is this upper bound tight or not? And actually it is, and we can show this by giving an explicit scheme with 4-dimensional entanglement assistance that achieves this value. Okay? So now we really know that this is entanglement assisted success probability. Of course, you can say, well, this is a very specific example. It's like the 3rd digit, right? Why should you care? But the point is the technique, okay? We were able to get a handle on the power of the quantum assistance. Okay, again, for the experts, so if one would just use these NPI hierarchy methods, then one would not have these positivity conditions on the matrix entries and would actually not get a bound. If you're interested in channel coding, more about this, there is this follow-up work by Barnum and Fuzzy, which I want to point to. Good. Now, very briefly, how are these ideas useful for cryptography? So here we really want to bound the power of a quantum adversary. And the setup we want to look at is for randomness extractors. So here's a task of private simplification. We have some weak source of randomness, okay, that only has some entropy. Well, technically it's min entropy, but then we would like to apply some scheme, some classical scheme that gives us uniformly random bits, like perfect uniform random bits up to some small epsilon, okay? So one way of achieving this is by using a set of 2 universal hash functions. But usually this is not exactly what we want to do. Actually, we want to achieve something stronger, right? We also want to get a handle on quantum adversaries. So we not only want to get uniformly random bits, but we want them also to be uniform relative to some quantum adversary E. So these tasks are, well, they're not the same. So this thing on the left-hand side here is called randomness extractor, where this is called quantum proof randomness extractor. And well, there is lots of motivation for studying these objects because, well, they're used in most of the cryptographic protocols we use. Quantum key distribution, 2-party crypto, And also, I mean, in general, classical cryptographic protocols, if you want to make them secure against quantum adversaries. Okay, so now I want to define the classical value of the extractor. This is just the epsilon we can achieve, okay? So if we use some extractor construction, the epsilon we can achieve, I call the classical value. And the epsilon we can achieve in the setting with quantum adversaries, I call the quantum value, okay? So again, I want to compare the error that the best possible error we can achieve, the classical setting and in the quantum setting, and I want to know how far are they apart. Are they the same always or not, okay? And again, this Q value, it's not clear if it's computable because we want to have channel adversaries. They're unbounded in dimension. Okay, so what we show in our paper is that in a very similar way as in the channel coding example, one can write this classical value of the extractor as a classical bilinear optimization and the quantum value as a quantum bilinear optimization, where these two programs are again the same, just in one time one has scalar variables and one time one has matrix variables. And then one can again apply the same idea. We can develop a hierarchy of semi-definite program relaxations, and there, at least the first few levels are efficiently computable, and this gives us an upper bound on the power of the quantum adversary, right? Because, for example, if this STP1 is already the same as the C, then we know that the Q has to be in between. Okay, so I don't want to give you any technical statements here because it's kind of heavy, but just point to our paper. Good, so let me wrap up quickly. So I guess the topic of my talk was to understand the power of quantum assistance or quantum adversaries using optimization methods. And the way we got a handle on these kind of unbounded problems was by using these STP hierarchy methods. And our hope is that we can apply this proof method even more generically, not only for these randomness extractors, but maybe for whole cryptographic protocols. Okay? Good. And the very last thing to say, this hierarchy we develop is also useful for other problems. Thanks for your attention.
Thank you. We have time for questions. Yeah, come.
I want to know if you have any sense for when in fact, the size of the variables you're optimizing over can be taken to be finite.
No, I don't. So you mean like a dimension bound, or no, in general, cannot show anything like that.
So you mentioned that you have one extra constraint compared to the NP hierarchy. Can you?
Additional constraints?
You have an additional constraint compared
yes,
to the NP
yes.
hierarchy.
So,
can you just comment quickly on this?
So in this first level, the additional constraint is really that all matrix elements, so every single element of the matrix is not negative. So I think in the NPI hierarchy, if you look at higher levels, you can also get that the off-diagonal entries are non-negative, but that the diagonal ones are non-negative, I think it's a qualitatively different constraint. For the higher levels, the hierarchies are different, but on the first level, this is the difference.
So let's thank Mario again.